online to talk to us about computation by quantum walks. And for the last day, we talk about a very interesting question. How hard are small problems? It's all yours, Viv.
Thank you. I assume you can hear me okay.
Okay.
Yeah, good.
We hear and see.
So I'm going to, how hard are small problems is one of the questions I'm going to tackle in the last tutorial. I'm going to go back and pick up some of the points that I slid over that maybe are questions about how well the things I presented actually work. And this is one of them. I'll give some insight into this question. So here's the overview of what we've covered. Starting out very generally and then looking at quantum walks in continuous time, solving optimization problems. In particular, we looked at spin glass ground states, which nobody knew that a quantum walk could solve directly until the relatively recent work we did. So this is the setting. We have quantum walks as one corner of a whole range of different ways to use continuous time quantum computing that smoothly join up and are using the same Hamiltonians and problem encodings. And we looked at search, which becomes a two-dimensional subspace in the large size limit, and you get the quantum walk is the this side of the graph, but you get the speed up all the way across all the variants over to here, which is adiabatic quantum computing. And so in the ideal case from this joined up picture, you can say that quantum walk is best. It's taking the shortest time and it's finding the solution with probability almost 1. Depending on how large your problem is. And then with the spin glass results, it's an almost opposite picture. You're finding in a short runtime, you're finding the ground state with some small probability, so you have to do many repeats. But you get a nice scaling for small sizes. Small here, this is the number of qubits, so the size of the problem space, the ground space, the description of the energy is 2 to the n, and 2 to the 20 is not so small, but it's still not asymptotic by any means. It's tractable on a classical computer to get these results. And we found that we can set the parameters quite approximately and still get a good scaling here. And we looked at why we managed to be better than search in this setting, because we're exploiting correlations in the spin glasses. So, but for small sizes, there are a couple of puzzles that I didn't go into in much detail. The first of which is search in this setting shows strong finite size effects. And we know asymptotically this probability should be 1. But at a size of 2 to the 45, we are still at maybe 97%, not. So we're not like 4 9s or 9 9s or something. We're still 3% away from the asymptotic probability. It's a very slow convergence here. And if we look at the same small sizes as we're looking at for the spin glasses, and we said, how does it scale? We would have no idea, because you get this shape here from 5, it goes down, and then back up again to 20. And we would have no idea whether that's a trend that is reliable or not from a section of the data that corresponds to this. So why is this happening? And more generally, can we use small systems to predict the behavior of larger ones, large enough to make a quantum computer worthwhile for solving them? So first of all, for the spin glasses, I will give you some reasons why we think that this scaling is reliable. And that is, first of all, even 3 qubits have frustration in the problem. So this is what I showed to explain frustration. If you want to get a low energy, and if the spins have to be anti-aligned to do that, when there are 3 of them, you cannot do this for all of the interactions. And so you always end up with something that is not satisfied or frustrated. Now, the weights in the Hamiltonian for this, we've drawn from a Gaussian distribution as real numbers or to whatever precision we're using if we're doing this numerically. And these 2 factors mean that for spin glasses, although this is an asymptotic concept, how hard the problem is, it's a problem that's uniformly hard. So almost all problems are hard as the hardest problems. And you can see that if you wanted to get an easy problem, you would have to draw very special values of the H's and the J's from the Gaussian distribution. And because it's a continuous distribution, it's a vanishing probability that you would get all of them to be special values. What it means to have these random values for the parameters is that you're avoiding degeneracy and exact cancellations when you're looking at these energies. So I drew this with none of these parameters in here, but in practice, each of these energies here will be multiplied by one of these randomly drawn parameters. So that might be minus 0.763 times minus 1, for example. And then you'll find that this sum here is not going to match the sums for any other 3. So you don't get cancellations. So those 2 things together suggest that for this problem, this scaling is going to be a good predictor of much larger sizes. It's not a proof, but it's good evidence that it's reasonable to think that this is the case. Now, clearly, it's not the case for search. We cannot use search to do this. And I will show you another problem where maybe we can when I get a little later in the talk. So now let's look puzzles for any size. So the way we're solving the spin glasses, we're doing short runs, just polynomial in n, so logarithmic in 2 to the n, and then doing many, many repeats. Now, this strategy cannot solve the search problem with a quantum advantage. It does not work to do this for search, but it does for the spin glasses. So why does it work for spin glasses? Does it work for other problems? And then after that, I will look at the heuristics, how to choose the parameters that you need without cheating, without having to first solve the problem that you then want to use the quantum computer for. So this is kind of a problem with oracles. If you don't have an oracle that already knows the solution to the problem, can you set up the quantum algorithm so that it will solve the problem? So for practical implementations, it's really important to be able to do this. You can analyze a problem and you can look at get its asymptotic scaling and understand how hard it is and many, many things about it. But if you want to use it on a real quantum computer, you must be able to actually set your problem up without solving it first. So on the first of these questions, why does it work for spin glasses but not for search? I can offer you the observation that it's got something to do with how fast the dynamics are when you run the quantum walk. So search and the random energy problem, the model that I contrasted with the spin glasses in the previous lecture, they both have slow dynamics. So the dynamics are running on the order of the problem size. So this is the peak if we're running a quantum walk, and it peaks at order square root of the problem size. And this is the spin glasses, and you are getting a much more rapid variation and a very fast convergence to the time average value when you do the time averaging. So this is converging in a time that's logarithmic in the problem size. So this is the observation. This explains why you can do many repeats here, but you cannot here. If I did something on a logarithmic problem size, I would barely have got away from the random guessing probabilities. So the same timescale of out to here in the search problem is somewhere stuck down in this bottom corner. But that's an observation. That doesn't really explain why you get fast dynamics for spin glasses, but slow dynamics for search. So what is it about the problems that determines the speed of the convergence, the fast mixing, if you like, on the graph of the quantum walk? It seems it should be a property of the problem, because I can make the spin glasses slow by changing the graph that the quantum walk is walking on from hypercube to complete graph, for example. But I cannot find a way to speed up search by changing the graph that you walk on or any other properties about it. So this is an open question, and it seems to be very much related to the dynamics of quantum walks on graphs and the interaction of this with the problem that you're trying to solve, which is determined by the weights on the vertices of the graph. So when you set up the problem Hamiltonian, it becomes the diagonal entries in the Hamiltonian, the matrix, the adjacency matrix, plus the problem Hamiltonian gives you diagonal entries, so they become vertex weights on the graph that the walk is taking place on. So there's an important open question. There are different problem types. How are they? It's related both to the problem itself and to the graph that the walk is taking place on. What are the conditions? What determines this? What answers the question as to why this works for spin glasses but not for search? And what other problems could it work for? What are the characteristics? So I promised that I would give you another problem that quantum walks can also solve. Spin glasses are not a special case. And you might wonder that we have the two very different problems, and you might wonder, well, are they particular instances and everything else is just sort of doesn't work? That's not the case. The more generic case is the spin glasses, and it's search that is the special case. And so here's a problem, another problem that quantum walks can solve, and all of the different factors that I showed you for the spin glasses, how to pick the gamma, the broad peak that you've got, so it's not very sensitive to the value of the hopping rate, the fast convergence of the time average, everything like that looks very similar to the spin glasses. So I won't show you all of the pictures of that. And you get a similar scaling if you use a quantum walk. Something better than search, but maybe 0.4 instead of 0.5, in 0.5 being square root. However, as I pointed out for spin glasses, scaling as the problem size to the 0.4 does not beat the best classical algorithm. You have to add more to make your quantum walk more powerful in order to do better. And we know ways to do this, but they've only been tested numerically. But for max 2-sat, there are have been SAT solver competitions for a couple of decades. And the classical algorithms we know about now are much better. Their scaling is something like 0.1 or less than 0.1 for the range of problems that they work on. So if we want to find a real quantum advantage, we need to deal with how good classical algorithms are in satisfiability problems. So what I'm showing you here, it's a scatter plot that is comparing how hard, by some measure of how long it takes or what the probability is of finding the correct solution. So how hard a set of 11 qubit satisfiability problems are when you look at a good classical algorithm, certainly not the best, but one that will give a measure of the classical hardness. How hard it is for adiabatic quantum computing, and how hard it is for quantum walks this way. And you can see from the shape of the blob that there are tails. There's a lot in the center where it's a similar hardness for all of them. But it's certainly not sort of the shape that you would get if the hardness was exactly the same for all three methods. And it was only a question of one of them was square root faster than the other, say. So there's something more interesting going on with the range of how hard instances are for this problem. Different instances turn out to be harder or easier for different algorithms. So this is in fact one of the ways in which SAT solvers are so very good. They use a set of different solvers, all classical, and they actually use machine learning to figure out how much time to allocate, how many attempts to allocate to the different algorithms in order to optimize how quickly they solve problems. This is known as a portfolio solver. And the question we are then asking in this paper is an archive preprint about to be submitted. How useful is it to add quantum methods to a portfolio solver? Do we get a net advantage if we do that, or has the classical algorithms got it covered? First, I'd better tell you the definition of max2 SAT as a problem. So here we go. We have a set of Boolean variables, xj. We have n of the variables, and we have m clauses here. We have relations between the Boolean variables. We have or and then we have the unit single, which acts between two variables, and we have the single one, which is negation. You can always manipulate an expression made up of these operators into something called conjunctive normal form. So in this case, because we're doing 2SAT, we will have two variables per clause. So here's a clause with x or 1 or x2. Then all of the clauses are and between them. This one has not x1 or x2. And the idea is that you're trying to make all of the clauses true at the same time, or if you can't, that's impossible, satisfy as many as possible, so the maximum number. So if you're just asking the question, can I make all the clauses true? So can I make the whole expression true? Then it's easy. You just flip variables and get to the end of the variables. You can do this in a way that will then tell you whether you've satisfied the whole thing. But if you're asking, I want the maximum number, the assignment of true and false to x1 and x2 that satisfies the maximum number of clauses, not all of them, but necessarily, but maximum number, that's an NP hard problem. However, it's not uniformly hard like the spin glasses. There's no real valued coefficients involved here. There's only integers. And when you map it into the Ising Hamiltonian, you've got an expression where you can get cancellations. You can also set up, depending on how many clauses and how many variables, some of them are easy to solve. If you have a lot more variables than clauses, then it's usually easy to satisfy all of them. And if you have a lot more clauses than variables, like there's a phase transition, then it's usually impossible to satisfy all of them, and then it becomes hard to determine how many you can satisfy. So this example, the maximum is 5 that you can satisfy, and it will be 5 of them will be satisfied when all of the variables x1, x2, and x3 are true. And it's a bonus if you manage to set the problem up in the Ising Hamiltonian. So it will also, the solution will also tell you how many clauses are satisfied. This is actually quite easy to do. You can set it up so that the energy of the assignment of true and false values that you find is an integer that tells you how many clauses are left unsatisfied. And from that, you can, of course, find how many are satisfied. The reason this is important is there are many applications of practical problems that can be mapped to this satisfiability, to max2sat and related satisfiability problems. So that's why such good classical algorithms have been developed. They have commercial applications in very diverse settings. And so there's a real incentive to get very good classical algorithms to solve the problems. Okay, so let's see what happens. I won't describe the mapping. The mapping to the Ising Hamiltonian is quite straightforward. You can represent true and false with 0 and 1, and then if false has energy 1 and true has energy 0, you can then map that to the Pauli Z operators in a very straightforward way. So you can do one clause like that. You then do a sum of the expressions for each clause, and that's your Hamiltonian. So here's what we did, but I'm showing you graphs here that are not just the scaling for all of the problems we tested on averaged. What I've done is I've broken it down into deciles, so every 10% division of the hardest and the easiest. Because the average scaling could look good because at the small sizes, there are a lot more easy problems than there are hard problems, and that would skew the average to look better than it's going to be when you get to bigger problems. So let's look at the spread of hardness and see what we get. So you can see there's a range of lines here. I could actually make this bigger so it's easier to see. Let's go up to something like that, or even a bit larger. Maybe we'll try that. There we go. So you can see we've got a whole set of lines here from light to dark, and then a green one. And there is a red spot here, which is a special data set that is hard for adiabatic quantum computing, which is an important motivation for why we did this, but not important to the story I'm telling here. And so you can see that the scaling, the line for the easiest 10% is shallower than the line for the hardest 10% down here. And then the green line is the hardest 1%. So each of these has been fitted to give the slope of the line, to give us the scaling. And so this graph here, this number here is the scaling, so the slope of this line. And you can see we are starting at about 0.4, so similar to the spin glasses. And as you get harder and harder, the slope gets worse and worse. And so when we get to the hardest 10%, we are worse than search for these ones. And the hardest 1% is down here, somewhere like maybe about minus 0.57. So now let's look this is the time it takes to get a 99% success probability for adiabatic quantum computing. And so we've got the same lines here divided into the hardest and easiest 10% and the hardest 1%, as measured as hard for AQC. So not as measured as hard for quantum walks, but measured as hard for adiabatic quantum computing. There's no single concept of hardness here, is important to note. In the paper, you can look at this plotted the other way on. So we take the hardness from quantum walk, and then we plot the AQC data and see how the scaling changes. Let's just keep it simple and look at this. So what we've got here is the slope getting worse. So we're not doing as well solving the hard problems as you'd expect. And over here, you can see that our scaling is something like 0.1. So lots of the easy problems are relatively easy. We're 0.1 or 0.2, so very competitive. Not so dissimilar to the best SAT solvers. And then as you get to the hardest ones, you get a very steep jump to above 0.6. So the hard problems are extremely hard for adiabatic, but the average to easy ones are easier than they are for quantum walk. So let me get back to my page so we can see the rest of the points here. So what we can see is that, yes, potentially, see the lines are splaying here. So as you get to larger sizes, there's a bigger range of how hard they are. So potentially, if we take the average of this, it's not going to be the average for larger sizes. That's not necessarily going to give us a completely reliable prediction for what will happen for larger sizes. But in terms of how to exploit this to get a quantum advantage, what we need to note is that the hardest problems take by far the most resources. If a classical algorithm can solve an easy problem, and in particular, classically, it's easier to tell whether the whole expression is satisfiable. Whereas for quantum algorithms, don't pick out whether it's satisfiable or not. So they do worse than classical on a subset of the problems. So what you want to do, if you want to have a good, an optimal algorithm, is you want to use classical algorithms to pick off the easy ones, and then adiabatic, because it's finding the easier problems easy too. If the problem's not succumbing to that, you want to go for quantum walk, because quantum walk is not finding the hardest problems as hard. So hybrid portfolio solvers, you could add a quantum walk algorithm to and work out, if you've solved the problem with an algorithm that picks off the easy ones, that's great. That didn't take you very much time. But the quantum walk could reduce the time you need for the really hard problems. And since that most of the resources is solving the hard problems, that will make quite a big improvement overall. So to say, what this is answering the question. It's not just quantum walks that you can do this short runs and many repeats for. It works for max 2 SAT. We've also tried it for maximum independent set. So the fairly standard problems that you try in an optimization setting, quantum walks will work for them. But whether you can work out what scaling you get from the small sizes depends on the problem. And we think for spin glasses that you can. For max 2 SAT, maybe, but with some caveats where you have to look at the hard and the easy. And in any case, how you want to use the quantum algorithm is not just necessarily in isolation, but you want to use it as part of a portfolio solver, because that is how the best classical do it, and you don't want to give yourself a disadvantage over what is already known to be a good strategy. Because the max 2 set problems are themselves not a uniformly hard set of problems. You get different characteristics in the different instances. So that sort has answered the question here. Does it work for other problems? It's given some insight into why it works for spin glasses, but there are open questions there. Now I'm going to talk about heuristics, how not to cheat. Oh, wait, before we get there though, very generically, the mechanism that's going on. So I've shown you that it does work for other problems, but why does it work? I have a little more insight for. Very, very generally, you can show that there's a mechanism going on that explains why these short runs work. Because if you stop and think for a second, quantum walks have energy conserving dynamics. We have a time-independent Hamiltonian. So the energy in the system that we start out with is the energy that you're going to have in the system at the end, unless you've got some noise or decoherence as well. But for a pure quantum walk, it's not at all obvious that you're going to increase the probability of measuring a lower energy state when the total energy of the system, a lower energy state with respect to the problem, not with respect to the whole Hamiltonian. So we want a low energy state with respect to this part of the Hamiltonian, but the energy with respect to the whole Hamiltonian has to stay constant because there's no time dependence in here. And so your first thought, if you're trying to do this, is this can't work because you can't change the energy of the total system. And you do with with quantum annealing, for example, you're calling it. But what happens goes something like this. We're starting in the ground state of the driver Hamiltonian. So that equal superposition over all possible states is the ground state of the hypercube Hamiltonian. It's the ground state of the complete graph Hamiltonian. It's the ground state of quite a lot of other graph Hamiltonians that you might want to choose for your quantum walk. And you started the ground state, and you started the ground state without really thinking about it. You start because it's the state of maximum ignorance. So you argue for it under for different reasons. But in fact, it matters very much that you start in the ground state from the point of view of the success of the algorithm. We're starting in an eigenstate of this part of the Hamiltonian. And these two parts of the Hamiltonian do not commute. So this is sigma z's and this is sigma x's, and they do not commute. So it's an eigenstate of this part. It will not be an eigenstate of this part. And when you apply the whole Hamiltonian, some dynamics must happen. If it's an eigenstate, nothing happens when you apply the Hamiltonian. But it's not an eigenstate of the whole Hamiltonian, and so you will get dynamics under the full Hamiltonian. So that means you must populate some higher energy states and some lower energy states than the one you started in. So the one you started in is here. But if you've got dynamics, the only way to do dynamics is to populate a superposition of higher and lower energy states and conserve energy. You will have some lower energy states populated, guaranteed in the way that quantum walks work. And they will be lower energy with respect to the problem Hamiltonian. So this mechanism generalizes to monotonic annealing schedules. So it generalizes across to adiabatic quantum computing that's run much too fast. So there are excited states involved. So what these pictures show, there's a light gray here that is showing you the success probability. And it's showing you the average energy with respect to the driver Hamiltonian in green up here, and the average energy with respect to the problem Hamiltonian in red down here. And you can see you promptly end up with a lower expectation value for the energy very soon after starting to run the dynamics. This is the same thing for the random energy model, and you can see the probability going up and peaking and dropping again. So it's like a very noisy sort of search. But notice that the time scale here is much longer than this one. So if I look at 12 units here, I've still got this effect going on with lower energy states, but I still have a very low probability of measuring the lowest energy state. So it's a very general mechanism. It works even for problems that are not solved on short timescales, although it's taking a slightly longer timescale to get here. There is a proof of this, so an analytical proof that of this mechanism, and I don't have time to go through the proof, but if you're interested in looking at it, it's based on analysis of the eigensystem for the different Hamiltonians. Essentially, what it's giving you is a very weak result. It's saying that if you run the quantum walk, you are guaranteed not to make things worse. You're guaranteed not to reduce the probability of finding the lowest energy state. Not going enough to prove that you're getting some advantage from this. What you also need is to ensure that dynamics happens on short timescales. So what we then do is look locally to see how well balanced the operators are for local subspaces, single spins if you like, but any local subspace more generally. We have a driver Hamiltonian on a map, on a graph, and where you have non-zero elements, which, in other words, where you have edges in your graph connecting nodes J and K, if that is non-zero, we can then look at this and say, we've got a two-dimensional subspace with J and K, our two states, our two nodes. How balanced are the operators between the problem Hamiltonian and the driver Hamiltonian in that subspace? And you can estimate this efficiently by sampling. So you can calculate from the description of the problem, either estimate by sampling or it's calculated exactly for some problems. And what you find is search in the large size limit has no short time dynamics. The dynamics all happens on long time scales. But for the spin glass, it's small, but it's bounded away from zero. So definitely get short time dynamics in the spin glass. We can use this so that we also have a way to set our global parameters for our quantum walk or for our quantum annealing. So this is how not to cheat. It's all in the same paper here that has the proofs. So we use these local subspace samples to set our global parameters. So we can take an average over the different subspaces by balancing the driver and the problem Hamiltonian. The way that you have to do this, I explained how we did it globally for the spin glasses, and that's essentially what you have to do very precisely to set gamma for the search problem. But now what we do is we look at these local subspaces and say, what would be the best gamma for this subspace? What would be the best gamma for another subspace? And then we average over them. And if you've got a broad set of gammas, a broad peak for the probability, if it's not too sensitive to the value, this will give you a good estimate to use for solving the problem globally. So we did this for the spin glasses, so here is the heuristic, the blue one is the heuristic gamma that I showed you for the spin glass results, and has been in some of the graphs I've been showing. let me see if I can find, so this one, this blue line here is the same blue line here, the result that I've been showing you in both in the talk so far. And then the red one is what you get from this local sampling. And you'll see it's very, very close. It gives us a way when we don't have a statistical description of the problem, but we can still sample the local values we need. It gives us a way to estimate the gamma we need to use to solve the problem. Do more than that, we can take the local samples and we can use it to say how fast do we want to change the Hamiltonian in adiabatic quantum computing. So if you don't know, your best guess is to do linear. There's no reason to do anything else. And if you do linear, you get over a certain time, you get a probability here that's something between 0.4 and 0.5. So if you do a little bit of optimizing using these local values, it tells you you can speed up here, but you need to slow down more here. And if you do that, you get at least a 25–30% increase in your success probability. So it lets you design an annealing schedule, a nonlinear schedule here, that just by using local information that it's efficient to determine. I have been giving the talks about work that's been done over many years, and I have mentioned papers with many of my collaborators on, but I would like to take a little bit of time to make sure that I explicitly thank the ones that made the most contributions to the work I've shown. So Sugato at UCL was key in the ideas that we could do the connection between quantum walks and adiabatic quantum computing. Nick has done much of that work and brought all of the expertise on quantum annealing and adiabatic quantum computing to the group. Dom was one of the, and Susan were key people along with Rob Wagner in developing the diagrams of what computing is that I showed you in Monday's talk. With Tino and Katie, some of the work on perfect state transfer that led to the quantum finite automata that can do language recognition. The universality of quantum walks for the discrete time quantum walk was done with Neil Lovett. With Ben, we did the top hat distribution way back that I showed you for as part of the history of using quantum walks to compute. James Morley did the work really showing that search in quantum walks and adiabatic quantum computing are two ends of a spectrum. Adam did the spin glass work and the proofs that of the local, of the energy mechanism and the local sampling that you need to do along with Nick. And Paya did the work on, along with Adam, did the work on Max 2-sat. So not all of these students are strictly mine. Paya is now, in fact, Nick's student at Durham. And James was a master student. He was neither mine nor Sugato's PhD student, but he did his master's project under our supervision. So there have also been many other master's and undergraduate project students working on different aspects of quantum walks. Some of them have made it into papers. Some of them are co-authors on the papers that I have cited. All of them contributed some piece to the ideas or to checking the results that made it possible to publish them with confidence. So some key points and some open questions. I think out of all of the background about computing in general, remember that the concept of efficiency is different depending on whether you're thinking of abstract models or physical computers. So there's not just one way to define efficiency. That quantum walks can solve optimization problems is a relatively recent result. It's important, and it connects quantum walks up into a much broader space of being both practical and theoretically useful. Solving optimization problems in general, not for search, you get short run times, many repeats, and you can get the parameters heuristically. This makes them practical for early quantum computing hardware. There are open questions, though, on what the conditions are for getting the fast dynamics that you need for this to work, because it does not work for search. And understanding this, whether it's a graph or spectral, as a way to understand it better and find and characterize those conditions is an important open problem. Generally, there are two graphs involved in thinking about solving problems using quantum walks. You need to use qubits. So you have an encoded space where you've got qubits and you've got interactions between those qubits. And you've got weights on the qubits themselves, fields on those, and you've got weighted edges, the interactions between them. So you then add a driver Hamiltonian on a graph of your choice. Hypercube is my choice, but it doesn't have to be only hypercube. And then that induces the graph and the dynamics in Hilbert space. So you now have the graph for the driver Hamiltonian and down the diagonal. So the diagonal, all of the problem becomes vertex weights in the graph in Hilbert space. So what the properties of these graphs are and the interaction between them determines both the encodings available and the dynamics. And there are many open questions to characterize which graphs it's possible to set this up for. The tense product structure of the qubit space then induces what's the subset of graphs that you then get in Hilbert space that you can use. And how do the properties of the graphs then determine how well you can solve the problems? The original reason for being so keen to do this mapping between quantum walks and adiabatic is that if you have a nice clean direct mapping that like we have, up to that point, all the proofs have been done by mapping them both to the circuit model. So it proved that, say, it's universal or that has the same scaling, but it doesn't give you any intuition for how it works between the different types, the different models. But if you have a direct mapping, then you can say, then you can then take results from quantum walks on graphs and carry them over to adiabatic and say, what does it imply for computing in this setting, and vice versa. So there are results, for example, on Erdos-Renyi graphs for search in that setting using quantum walks. That will have implications for how adiabatic quantum computing works on those graphs too. And so that, as I say, was our ultimate motivation for why this will be a useful thing to do, is that it means that we can connect results that are provable in one setting, implies that there should be results that are provable in the other setting. So it opens up the relevance of graphs, quantum walks on graphs, to a wider class of quantum computing where it may provide proof method. So that's it. I have ticks on everything that I said I would do. And thank you very much for all of you for hanging in there. I'm sure what I've been presenting is well outside your comfort zone, but I hope I've given you some very small hooks for things to take back in to the mathematics of quantum walks and graphs that you know much better than I do, to see if you can produce some results maybe in directions you hadn't thought of or hadn't thought were interesting to the wider quantum computing community. So thank you very much.
Any comment, any questions?
Hi, this is Bill. Can you hear me?
Yes, I can hear.
Thanks for your talks. So I'm interested in this max two set issue. And my understanding is that the D-Wave machine, by some kind of annealing, gets good solutions to max two set. But semi-definite programming gives approximation to max two set that's 94% of optimal. So semi-definite programming does very, very well with max two set, and it doesn't do well with many other NP-hard problems. And there are NP-hard problems that are hard to approximate. Is there something going on that the hard problems, well, I mean, inside this optimization world, that we can solve might also be things that semi-definite programming can solve? Or could semi-definite programming simulate what the quantum process is doing, or vice versa? Could the quantum process maybe be universal for semi-definite optimization?
Yes, quite possibly. So we, of course, had to look quite hard at the classical algorithms to do this work. And the semi-definite programmer that they came up with for in this setting is called MixSat, and it's so it involves it's optimizing unit vectors, basically, which the standard methods don't treat well until they figured out how to do it for unit vectors. But of course, unit vectors are really rather like qubits, only they're in real space, right? So they basically, the classical bits are relaxed and allowed to point in any direction, which sounds awfully like a qubit. So it may well be very, very related that the mechanisms in this case, the mechanisms that the quantum computer is using and the mechanisms that the semi-definite programming are using are actually closely related for this type of problem. Now, how much that generalizes, I don't know. The semi-definite programming experts are way off, way from the quantum computing experts in terms of connecting up the two sides of that problem. But you've correctly identified that there's something very interesting going on in this particular case that I have not been able to look more closely at, but I think it would be very, very fruitful to burrow a little further down this path and find out where the similarities are and where the differences are.
Yeah, I think, I mean, in my opinion, I mean, comparison to SAT solvers isn't fair, because SAT solvers have been optimized and thought about for a very long time. But this SDP sort of off-the-shelf solution to max 2 SAT suggests that this is something that really is very, very easily approximable by an exact technique. So I just wondered what you thought about that. Are there other types of optimization problems where quantum approaches and semi-definite programming are competing? Are there other examples that we know of where both semi-definite programming and quantum algorithms give fairly reasonable approximations?
No, to some extent, that is a current topic of research, but I'm funded to look at different classes of algorithms currently, ones that would simulate fluids or simulate materials. So rather than ones that sit in this optimization space. I mean, there is an intersection because some of the material simulations are also optimization problems. So we may well be able to dig into it further. But it's currently something that is, as you say, it's a very interesting problem, but I don't have more. I think you probably have looked closer at that than I have at this point. I would definitely be interested to talk more about it.
Thank you.
Any other question? If not, let's thank again